Hey guys, is this recording? Yes. Hey guys, so today for Lab 8, we're going to go over correlation. And on the lab sheet, the first question is going to show you a set of scatter plots, and your job is to interpret these scatter plots. I'm sure you'll do something in class with this, so it should be pretty intuitive. But just a brief review, since some of you might be learning this for the first time. When you look at these scatter plots, you should consider three things. Consider the form of the scatter plot. So think about like how linear or non-linear the data is. Like you can see we have some data that's just like random. It doesn't really look very linear at all when you compare it to something like C, for example. So this is linear data right here. This would be non-linear. Uh, Also consider the strength. So um, the strength of association you can tell by looking at how the data points or the subject are clustered around like a line, like a best fit line. So if you're comparing B and C, C has a stronger association than B does because you can see how close these data points are to the mean as opposed to B. Uh, Another thing you should consider is the direction. So basically, which way, like, are you seeing a positive association or a negative association? A positive association is when two variables increase. So, like, as a person gets older, they become more intelligent. So you can see, if a x-axis was intelligence or age maybe, and then the y-axis here was intelligence, you could see that they both increase together, and that's where you get this line. Conversely, you can have a negative association, so that's when one variable is increasing while the other is decreasing. So trying to think of an example on the fly here. Uh, Number of friends equals less time alone. So less time alone would be the y-axis, and then more friends equals the x-axis. So as someone has more friends, they have less time alone. And it's probably not true, but um, yeah, just to illustrate this relationship. So essentially, going back to it, a positive association is two variables increasing simultaneously, and a negative association is when one variable increases while the other decreases. Uh, there's also no association, which you can see right here on the bottom. So um, when you look at these graphs, and I know I gave you the answers here, but try and consider why these are like YE is considered a perfect negative association. Well, it's considered a perfect negative association because of the form of the data. So it's linear. The strength, it's a perfect negative association because look at how these data points kind of like line up together around the mean, as opposed to A, for example, which has a strong negative association. And then the direction as well. So it's negative because one variable is increasing while the other is decreasing. So again, look at um, the direction of E compared to A. They're both still negative. It's just that one is stronger. One is more perfect than the other, or stronger, I guess you should say. Um, D has no association because it's not linear. So we have it's scattered out. The strength, there is no strength because like one variable is increasing, or I'm sorry, that's the direction. The strength, they're not clustered around some sort of like line or average. They're just kind of like spread out everywhere. And then the direction as well. It's not really like, it's not positive, it's not negative, it's just kind of randomly scattered about, not randomly scattered about, but it's kind of scattered about. So we would say no association. Okay, let's get to the good stuff. So for question 3, you're given an Excel spreadsheet, uh, and you're supposed to make scatter plots that show the relationship between different variables. So our dependent variable is going to be height, and then these are our independent variables: average parent height, income, and calcium. So you'll need 3 separate plots. We're going to go over 2 of those plots right now, um, or during this video. And for each plot, you should do exactly what we did in question 1 here. Oops. So you're going to be going over the form, the strength, and then the direction for all of the variables in question 3. You're going to do this in R, and you're going to need 2 packages. So you're going to need Haven, and you're going to need ggpub or ggpubr. You should have this one already, ggpubr, and I believe Haven as well. But if you don't have it, just make sure to triple check before, double check before you start doing any of this, because you're not going to have a good time. So this is the syntax. I put it here so you guys could see it a little bit better. But once we've enabled these packages in R, and I'll show you what's going on in R in just a second, this is the command that we're going to give: scatter, ggscatter. I've titled my document lab 8 height. Even though the Excel file just reads height, I did it so it wouldn't be confusing, because we have height as our dependent variable here already. So this is the title of the Excel spreadsheet. The first question is asking you about average parent height and height of that person that was sampled. And you'll see that this line of syntax is the same as this one here, but we've added a couple more commands to it. This is going to give us an actual regression line, so that we have some sort of numbers to work with. Like, we don't just have to look at the scatter plot and interpret like we did with these over here. It'll actually give us like a correlation and a p-value, an R and a p-value. And then we're doing a correlation coefficient, so it's true. And then the method that we're using is Pearson, but there are other methods of correlation, like Spearman, for example. But you'll only need Pearson for this class. So let's get to it. So again, you're going to need these 2 packages here, Haven and ggpubr. For those of you who like to just type it in, you can do that. I just like to check them off, honestly. Like, I'll go to the packages library and just see where they are. And they should be checked off. I checked them off earlier, but like ggpubr, for example, is checked. Okay, so we have our data set that's been imported already. We do ls, and then the name of the data set. And so these are our variables here. A lot of you had trouble, some of you, I shouldn't say a lot, some of you had trouble entering in variables from your data set. Make sure when you enter them in R, like, you can see the X variable, how it's spelled. Again, R is case sensitive. So if this is how I've titled average parent height in my Excel spreadsheet with a capital A, I want to make sure that it's typed into R the exact same way. So it should be a capital A, and then the rest are lowercase letters. So now, I'm going to show you guys the difference between these two commands. So this is the first one that I was telling you guys about, just to get the scatter plot. And you can see these points here, and it looks like there's positive, some sort of positive association. Looks like it could be moderate, but let's be 100% sure by throwing in this command, or the rest of it. So the regression line, it's going to give us like the best fit line, and then a correlation coefficient, and then we're using Pearson's correlation. So you can see this popped up. So our R is 0.8, which is strong. Our p-value is less than 0.001. And you can see, like, remember the correlation is going to span from -1 to +1. So if we're at 0.8, it's pretty strong. Yeah, and it's a positive association because it's not negative. So let's go back. Could be kind of confusing going over this stuff in R. So this is the same exact graph that you guys just saw. It's a moderate correlation. I mean, moderate is, you could say moderate to strong. It's positive because two variables are increasing simultaneously. So average parent height is increasing as the individual's height is increasing. And then it's linear, as we can see here. Now, let's go to the next question. We're going to do the same exact thing. So for this one, we're going to do income and height. It's going to be quite literally the same exact line that you typed up here. The only thing that you need to do is just change your x-axis to whatever independent variable you're looking at. And then we can run it, and then we get something that looks like this. So we have our regression line, we have our correlation coefficient, and our p-value here. And let's go back to our presentation. So it's going to be, there's somewhat of a line here. I mean, you can see kind of these data points are scattered about over here as opposed to these, or compared to these. You could say like linear to nonlinear. And then as far as the direction goes, it is positive, but compared to this one, like this is for sure positive right here. You can see that the slope on this compared to this one is much greater. So you would say like positive or slightly positive for this. And then as far as the strength goes, it's weakly correlated. Aside from you having the R value and the P value here, you can kind of see in terms of the strength, because these data points are not clustering around this like best fit line here. They're kind of scattered about. So pretty simple. Question 3. Question 4 builds off of question 3, and for each one of those scatter plots that you were supposed to make, so I did 2 of them. I believe there are 3, so you guys will do the third one. For each of the scatter plots, you're going to make a prediction about the strength. Well, didn't we do that already? Yeah, we did. So we've already made a prediction about the strength, the direction, strength and direction of the relationship. Now we're going to use R to like write this answer in APA format so it makes sense. So this is the syntax you're going to use. You're going to see the same thing in R, but I just wanted to throw it on the presentation just so you guys could see it a bit better. And so these are our 2 variables here, average parent height, and then the height of our subject. I'm going to name this result 1. you'll see there's also syntax for like a result 2 and then result 3. You can name this whatever you want as long as you remember which question it corresponds to. We're doing correlation test, and then our x-axis, again, this is the name of my spreadsheet. Make sure you're entering in whatever you've named the variable in your spreadsheet onto R the same exact way because it's case sensitive. Our y-axis here, and then again, we're using the Pearson. So there are a couple of different ways you can get the output here. You can either just do, you can use this syntax here. So it's the estimate would just be our p-value, and then our parameter is the degrees of freedom, and then oops, I'm sorry. Our result 1 estimate is going to be our R value. The parameter is going to be degrees of freedom, and then this is obviously going to be the p-value. So these are the only 3 things you'll need to write your answers in APA. You could also just use this command right here, str, and then result 1, whatever you've named it over here. And I'll show you guys what it looks like in R right now. So we have this. I just showed you guys that on the previous slide. And I'm going to run this the first way to do it. So here we have our correlation. We have our degrees of freedom. And then we have our p-value, which is less than 0.001. Conversely, you can also do it this way. And this will just give you everything that you need. So you can see that everything that we did over here is going to be found here as well. There's just a bit more information. So our parameter is 38. The p-value is less than 0.001. This is really, really small. It doesn't say 0.001, but this, like if you did that math, it would be really, really small. And then for the correlation, it's right here, 0.8. So it even rounds it up for you, which is kind of cool. And then we have these outputs here. So this is going to be our APA style answer. Very easy. Height and average height of parents were strongly positively correlated. So same thing we did in the scatter plots, but now we just have values to work with. And it's strongly positively correlated because it's a positive value, right? 0.8 out of 1, that's strong. And then moderate to strong, and then, or you could just say strong, and then our p-value is less than 0.001. 0.001. So that's what we got, and then we'll do another one here. Same, almost the same exact thing to a T. The only difference is we're going to be using income now for our x-axis. And again, you can get these results in one of 2 ways. So let's go back to R. And then we've got this here. So I just copied and pasted this syntax over here and quite literally just changed the x-axis. So now we're going to run it. And you can see we get the same exact information over here. So we get the correlation, degrees of freedom, and then our p-value. And then this information can be found over here as well. So height and current household income were weakly positively correlated. It's weak because it's 0.25, it's pretty close to 0. And then, I mean, our p-value isn't even significant here. So it's definitely weak. Like it's not below 0.05, but it still has a positive correlation. So it still gives us information about the two variables um, in question, which is better than having no information. So yeah, that's what we got today. Um, the other question is going to be the same exact thing. Whoops. I believe there's going to be a question that you do by hand, similar to what you've done in class for figuring out correlation. And that one's pretty self-explanatory. And then a couple other questions where you have to think outside of the box a little bit. For one of them, there's no wrong answer. And then for the other one, I believe you're just deleting a data point off of your Excel spreadsheet and then running that um, correlation test to see if the relationship changes from taking out that outlier. So that's all I got. See you guys in lab.